Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the fourth element in the periodic table, beryllium. I have a sample of it right here in this file. It's so light I can hardly tell that it's there. Let's get back to our slides. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. As I mentioned, beryllium is the fourth element in the periodic table. Its atomic number is 4 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. In a 1798 paper read before the Institut de France, Louis-Nicolas Vauquelin reported that he found a new earth, or oxide, by dissolving aluminum oxide from emerald and beryl in strong alkali. He's given the credit for discovering the element beryllium, even though he never saw the actual metal. The editors of this journal named Vauquelin's new earth glucine for the sweet taste of some of its compounds. Martin Heinrich Klaproth preferred the name beryllia due to the fact that these substances formed sweet salts. It's somewhat of a miracle that any of these early chemists survived to old age with all the tasting going on. Frederick Wohler gave us our current name for the element, beryllium, from the mineral beryl from which it was refined. Frederick Wohler and Antoine Bousset independently isolated beryllium in 1928 by the chemical reaction of metallic potassium with beryllium chloride, like you see here in the formula. The result was metallic beryllium. The mineral beryl appears in many forms. Here you see a common non-crystalline form as an ore mined for its beryllium content. Beryl is a beryllium aluminum silicate. It does form beautiful crystals, such as the green crystal in this sample. The green crystalline form is called emerald and is fairly rare, actually more rare than diamonds. So you won't be seeing entire cities made from this stone, maybe over the rainbow in Oz, but not on our real-life Earth. Principal mines where emeralds are found are in Colombia, Brazil, and Zambia. This is a rough emerald from Colombia. The green color of emeralds is caused by a small impurity of the element chromium within the beryl. This is a small cut emerald I photographed. Teodora is a 57,500 carat stone found in Brazil and cut in India. As you can see, it's the size of a watermelon. There's some debate that this stone may be a white beryl that was dyed green. This is the Bahia emerald. It's among the biggest ever discovered, weighing 380 kilograms or 840 pounds, and has been involved in a series of dramas that could serve as a basis for a television series. It was found in a mine in the Brazilian rainforest more than a decade ago and had to be moved with a team of pack mules, one of which was killed by panthers. It was taken to the United States and stored in a warehouse in New Orleans. That warehouse was flooded by Hurricane Katrina in 2005. The emerald was moved to another warehouse in Los Angeles, but was stolen from there. The gem was then said to have been involved in a transaction involving a notorious Colombian family that nearly resulted in a bloodbath in the Nevada desert. It was reportedly involved in a $197 million banking transaction with Bernie Madoff, who was arrested by federal agents 2 days before the transaction was completed in 2008. The emerald was next sighted briefly in Idaho before authorities seized it in Las Vegas. The Los Angeles Sheriff's Department currently has it under lock and key. Depending on impurities within the beryl, there are many possible colors, as you see here. An iron impurity gives beryl a yellow color. This is called golden beryl. And then there's aquamarine, whose blue color is also from an impurity of iron, but ionized differently. Chrysoberyl, which is a beryllium aluminum oxide, is a very interesting mineral. Here you see it in its natural crystalline state, beautifully reminiscent of snowflakes. It's also known as alexandrite, which has some unique optical properties. Under sunlight, an alexandrite stone can appear greenish, but bring it inside under incandescent light and the same stone will appear pinkish. This has to do with the qualities of the incident light and how alexandrite absorbs some specific colors. One last beryllium-containing mineral is bertrandite. It's a beryllium sorosilicate hydroxide mineral with this composition for all you chemists out there. In addition to beryl, this mineral is also mined for its beryllium content. Beryllium is a member of the alkaline earth group. Like magnesium below it, beryllium has 2 valence electrons in its outer S shell, which is now full, so its electron configuration is 1s2, 2s2. The next element, boron, starts to fill the p shell. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 4 protons for beryllium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 12 known isotopes of beryllium, and of these 12, there's only one stable, non-radioactive isotope, beryllium-9. Beryllium is therefore a monoisotopic element. There are 23 of those, by the way. The stable beryllium-9 isotope obviously makes up all of the naturally occurring beryllium in the universe. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of beryllium occupy the same place in the periodic table. Most of the radioactive isotopes of beryllium are very short-lived. These are the 3 longest-lived ones with half-lives over 1 second. More on half-life in the next slide. The longest-lived is beryllium-10 with a half-life of about 1.4 million years. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide, even the short half-lived ones. If you wait 1 half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait 1 more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's 1 remaining atom after 10 half-lives. If you waited 1 more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Even though beryllium is the 4th element in the table, it's pretty rare, coming in as the 65th most abundant element in the universe by mass, only 1 part per billion. 1/10 as abundant in the Sun. It's the 73rd most abundant element at 1 part per 10 billion. Only lithium is less abundant in our star. It's the 76th most abundant element in meteorites, again near the bottom of the chart at 2.9 parts per 100 million. The crust of the Earth is a virtual treasure house of elements. Beryllium is the 50th most common element at 1.9 parts per million, 24 times as common as silver. Beryllium is the 61st most abundant element in the oceans, virtually non-existent at 600 parts per quadrillion. And lastly, surprisingly, there's a bit of beryllium in us, probably absorbed from the environment, only 4 parts per 10 billion. This amount is not considered hazardous and serves no known biological function. Beryllium is very light. Its density is only 1.848 grams per cubic centimeter, slightly less than double that of water at 1 gram per cubic centimeter. I've put up a few more elemental densities so you can compare. Note that beryllium is about the same density as magnesium at 1.74 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. When I do this talk with an actual audience, I have a set of blocks so you can feel density for yourself. My blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, beryllium's density is 1.848 grams per cubic centimeter, the magenta circle, slightly above the density of magnesium. Beryllium melts, or conversely freezes, at 1287 degrees Celsius, or 2349 degrees Fahrenheit. It boils at 2470 degrees Celsius, or 4478 degrees Fahrenheit. That's 1183 degrees Celsius above its melting point. That's kind of a middling liquid temperature range among the elements. If we compare the size of the beryllium atom to that of hydrogen, we'd see something like this. The beryllium atom is a little over twice the size of hydrogen. By the way, a picometer is a trillionth of a meter, so atoms are very, very small. Here our atom sizes sorted from largest, cesium at the top left, to smallest, helium at the bottom right. Beryllium has a smallish sized atom, mainly because of its simplicity. Notice that many of the early elements in the periodic table are found in the lower right of this chart, except for the alkali metals, which are generally fairly large. About 2/3 of the world's beryllium is produced in the United States. China is second with about 27%, Uganda with almost 3% is third, and everybody else, Brazil, Mozambique, Nigeria, Madagascar, and Rwanda with the remaining 3.5%. Here you see the world mine production of beryllium between 1936 and 2019. On the average, the world produces around 200 to 250 metric tons of beryllium per year, though as you can see, production has its ups and downs. Beryllium isn't cheap, going for about $1,000 per kilogram. Remembering price depends on quantity you buy and its purity. Of course, because of its low density, you get a lot of beryllium volume-wise for its weight. Here are the historical prices of beryllium from 1936 to 2019. I don't know what caused the drastic drop in price in 2000, but it has recovered and is now around $1,000 per kilogram. Beryllium is a medium-hard element, coming in at 5.5 on Mohs scale of hardness, harder than iron at 4 and a bit softer than stainless steel at 6. Beryllium is really stiff and springy stuff. Sound, therefore, moves through beryllium really fast. It's the third fastest element after carbon in the form of diamond, and our next element, boron. Sound moves through beryllium at an astonishing 12.8 kilometers per second, over 37.5 times as fast as sound moves through air. Beryllium does not expand much when you heat it. It has the 32nd highest rate of thermal expansion, about 11 parts per million per degree Celsius. This means that if you had a 1 meter long bar of beryllium, and we'll magnify this by a factor of 10 just to see it, and you heated the bar by 1 degree Celsius, it would get longer by only 11 millionths of a meter, about 1/5 of a hair width. This is important in some applications, as we'll see. Okay, last graph, I promise. Beryllium is pretty good at conducting electricity, though nowhere as good as silver or copper at the top of the chart, which both are about 2.5 times as conductive. Beryllium is still the 6th most conductive element. Here's the periodic table of the spectra. Beryllium has a relatively simple set of emission lines which uniquely identify the element to scientists. No other element gives off these specific colors when excited. Okay, last graph, I promise. Beryllium is a pretty good conductor of electricity, though nowhere near as good as silver or copper at the top of the chart, which are 2.5 times as conductive. Beryllium is still the 6th most conductive element. Here's the periodic table of the spectra. Beryllium has a relatively simple set of emission lines, and these uniquely identify the element to scientists. No other element gives off these colors when excited. There wasn't enough time during the Big Bang to create elements beyond lithium, so much of the beryllium present today is created between the stars from atoms that make up the interstellar medium. The process involves extremely fast-moving particles called cosmic rays. They can crash into larger atoms, such as carbon, and break them into smaller pieces. This process is called spallation. This also creates beryllium atoms on Earth by cosmic rays interacting with oxygen and nitrogen atoms in our atmosphere. The production of carbon in the universe also involves beryllium, albeit briefly, in something called the triple alpha process. Near the end of a star's life, it has burned much of the hydrogen in its core and turned it to helium. The star compresses, heats, and starts using that helium to make heavier elements. Let's move inside the star's core. In the triple alpha process, 2 helium nuclei collide to form a beryllium-8 nucleus and a gamma ray. Even though this isotope has a half-life of only 82 attoseconds, that's 82 quintillionths of a second, 82 times 10 to the minus 18th seconds, the star's core is so hot at 100 million degrees and so dense that there is a probability that yet another helium nucleus will collide with the beryllium-8 during its short life and create a carbon-12 nucleus and another gamma ray. This carbon, along with other elements, is often spread into the interstellar medium when the star ends its life as a nova or by creating a planetary nebula. Turns out that if you shoot an alpha particle at a sheet of beryllium, neutrons are knocked out. The helium nucleus, the alpha particle, fuses with a beryllium-9 nucleus, creating a carbon-12 nucleus and a neutron. Here, I've used a piece of radioactive uranium ore called carnotite as an example alpha source. In practice, the radioactive alpha source is typically plutonium or americium. This is not an entirely efficient process. You get only 30 neutrons out for every million alphas you send in. Using this apparatus, with polonium as the alpha source and a beryllium window, allowed James Chadwick to discover the uncharged neutron particle in 1932. He received the Nobel Prize in Physics in 1935 for this fundamental discovery. Let's take a look at a few of the many applications beryllium is used for. Beryllium has many applications because of some of its desirable properties. A few I list here. It's very stiff and springy. It has a low density. It conducts heat very well, does not expand much with temperature, and X-rays go right through it. Beryllium is the perfect material to make speaker domes from. In a speaker, inertia is your enemy. You want your speaker cone to respond as quickly as possible to the electric signal you feed it. Beryllium is so light, it responds quickly and does not bend or distort because of its stiffness. Telescope mirrors made from beryllium, like the mini segments of the James Webb Space Telescope you see here, are very resistant to temperature change, not changing their shape when the temperature varies. In the Webb's case, the silvery beryllium mirror is coated with gold to reflect infrared light. Beryllium also performs well at very low temperatures. Webb's mirrors are kept at only 40 degrees above absolute zero. Here, you see the backside of one of Webb's mirrors during manufacture. Beryllium's low density, and hence low weight, was an important aspect of the telescope since it was launched by a rocket to its destination. Every gram saved in the weight of the mirrors could be used to launch more scientific instrumentation. Beryllium was the perfect material. Beryllium and beryllium alloys are the metal of choice in many military applications because of its lightness, stiffness, and thermal properties. A lighter aircraft saves fuel, is more maneuverable, and can travel farther and faster. Beryllium's also used in guided missile defense systems. In the movie Galaxy Quest, one of my all-time favorites, the starship is powered using a beryllium sphere.
The generator room, the beryllium sphere, of course.
Coming back to reality, beryllium spheres are actually used as part of military gyroscopes to guide missiles. The sphere is hard and stands up well to heat generated by its levitation. Also, it does not expand much when heated, very important for a delicately balanced mechanism. Speaking of science fiction, Isaac Asimov wrote a novella called Sucker Bait, where beryllium plays a role. The 2 volumes of astounding science fiction, where the story appears, are available from the Internet Archive. Please, support the Internet Archive. It's important. X-rays are typically generated by smashing fast-moving electrons into a stationary target in a vacuum. Here, the X-rays exit through a beryllium window. Beryllium is almost transparent to X-rays because of its low density and atomic mass. Its stiffness also allows the windows to be very thin. Thinner windows transmit more X-rays. Likewise, an X-ray detector has a beryllium window to exclude everything but X-rays. Beryllium, added to copper, makes an alloy that's stiff and hard enough to make tools. Here is a representative sampling of beryllium-copper tools. In some environments, you don't want your tools to make sparks if they slip or hit things. This would be true if there were flammable gases or dust present, like in the mining or oil extraction industries. These tools are also non-magnetic, so will not disturb sensitive instrumentation or be attracted to strong nearby fields, such as when working near an MRI machine. You don't want your hammers flying through the air near million-dollar machines. Apparently, there are golf clubs made from beryllium-copper alloys. This is certainly a cultish, boutique, and unnecessary application of this alloy. Beryllium oxide is useful for many applications that require the combined properties of an electrical insulator and an excellent heat conductor with high strength and hardness and a very high melting point. Here you see the internals of a gas laser. While some of these are made from glass, this one's tube is made from beryllium oxide. The beryllium oxide is a very good conductor of heat. These lasers typically use 10,000 watts to produce the plasma inside the tube, but only output 1 watt of light. That means the cooling system must remove 9,999 watts of heat. The high heat conductivity of beryllium oxide makes efficient heat transfer possible. The earliest fluorescent tubes employed a phosphor of zinc beryllium silicate, the first material found to create white light with reasonable quality. However, the efficiency of the popular 5-foot tube using these materials was just 35 lumens per watt. Current tubes are almost 3 times as efficient and produce 85 to 95 lumens per watt. This use of beryllium compounds was discontinued in 1949 because of the disease berylliosis, which developed in workers who were making the tubes. Beryllium exposure and toxicity can cause serious acute and long-term health effects. Inhalation of beryllium dust causing berylliosis, or scarring of the lungs, is a permanent and untreatable condition. Once in the lungs, beryllium is impossible to remove. As I mentioned previously, there's a bit of beryllium in us absorbed from the environment, only 4 parts per 10 billion, but as far as we know, it serves no known biological function. As usual with my element talks, we'll end with Mary Soon Lee's elemental haiku about beryllium. Heart of emerald, your sweetness a toxic trap. X-rays see through it. In the next program in this series, we'll examine the first of the semiconductor group, the element boron. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element beryllium.